Alright, so the first section that I'm going to talk about is an introduction to linear systems of linear equations. So linear algebra starts with the study of systems of linear equations, and then it gets more in depth and performs more algorithms from there. So as a quick reminder, first of all, what is a linear equation? A linear equation is anything that can be written as ax plus by equals c, where a and b and c are elements of the real numbers, or they're constants. So remember, we've seen this in algebra as y equals mx plus b, small b, sorry. Or we've even seen that this is the standard form in the first one. This is the slope-intercept. We've also seen it as y minus y1 equals mx minus x1, and so on. This is point slope. Now, this equation is called linear equation in two variables. As you can see, the only variables we're working with, x and y, are the ones that are not constants. Now, and this is in the two-dimensional space. But in 3 dimensions, we have a x plus b y plus c z equals d, where again a, b, c are real numbers, and so is d. Now, and normally when we're in the third dimension, there's times where we just solve for the z variable. So if we solve for z here, subtract ax, so it's z equals d minus ax plus by, and then it's all divided by c. So again, this is a linear equation in 3 variables. 3. And notice my abbreviation for equations here and here. Now there's a different form that they represent them as we can represent them. Instead of just x and y, we can call it x1 plus x2. This is linear equation in 2 variables. C, where c is a constant. Or in the third dimension, we have x1 plus x2 plus x3. And again, we could have coefficients in the front of these. And then it keeps going on in higher dimensions, or higher variables. So we can have a set way. So a linear equation in n variables, say x1, x2, all the way to x sub n, has the form a sub x1, a sub 1 x sub 1 plus a sub 2 x sub 2 plus so on, plus a sub n x sub n equals b. And again here, a sub 1 through a sub n are constants. And this r, I should have, this means a real number. So this is our pointer. So we can represent this any linear equation in a variable. So in 3 variables, we've seen it up here in the rectangle, and in 2 variables, we've seen it here in this spiky cloud. Now in this form, the terms a sub 1 through a sub n highlighted in orange are called our coefficients. And then we have in green, we have our constant, which is just b. So constant And then our x sub 1 through x sub n, those are our variables. Now, we also have a sub 1 being our leading term. So let me change that. So in this case, a sub 1 is the leading coefficient, and x sub 1 is the leading variable. And this is based off the order of it. So x sub 1 is first because of the 1. Well, let's see some examples. Let me just start here. So now some examples of linear equations of both linear and nonlinear. So linear equations. So example 1, part A, we have, say, 5x minus y equals 12. That is one example of a linear equation. Again, it's two variables, and they're not raised to any power. Another one we have is x sub 1 plus 2x sub 2 minus 50x sub 3 equals 0. That's a linear equation in three variables. What else? We can also have 1/2 x plus square root of 2y plus ez, where e is the regular e value, 2.1 or 2.7, whatever it is, equals 0. So that's another example. A non-example, so these are linear. Non-examples would be, say, something like y equals, or x squared plus y squared equals 4. That's a circle, so we're not dealing with those in this class in linear algebra. We also have products. So say we have xy plus z equals 20. We can't have any products. That's not a linear equation. F can be e to the x minus 3z equals 4. We're not working with any exponential functions or logarithms or anything like that. G is 1 over x minus plus 2 over y equals 20. This is not a linear equation. And last example, similarly, we're not working with any trig functions, so sine of x sub 1 plus x sub 2 equals 5. That's not a linear equation. So all of these below, non-linear. Just to cut that off there. All right. So now the conversation goes into solving for these linear equations. So when you solve for a linear equation in n variables, this is an important note, solving for n variables requires the solution to one equation to suffice for all other equations in the system. Meaning, if you solve for one equation, so let me write an example. So example, x plus y plus z equals 1. X 2x plus 2y plus 2z equals 2. And with third equation, x plus 1/2 y plus 2z equals 2. Now, one possible solution could be 0, 0, 2. Oh, I apologize. 0, 0, 1. And if this is an actual solution, so say I did arithmetic and I got it from the third equation, then I know it worked for the third equation. If I plug in 0, 0, and 1, 2 times, this first term will be 0, this will be 0, 2 times 1 is 2, which is correct. Well, if it works for this one, it has to work for the other ones. So it works for this one. Now it has to work for the second one. So now if I plug in 0, 0, 1 in there, does it give me back 2? Does the solution work? It just so happens it does. Same thing for the first one. And it's one solution for the first equation. Therefore, a solution to the system would be 0, 0, 1. And this is just a random example. I just try to make it as easy as possible. But that's the concept of a solution. And a solution has to work for all three of them. That's the gist. All right. Well, there comes a situation where sometimes the system won't give you enough variables. So let's change the color to this. Right? Now, if there is more variables than equations, then a parametric representation may be necessary. What does that mean? So say they gave you a system called x1 plus 3x2 equals 6. And they told you, find the solution. Well, one option is we could find some pick and choose variables. x1 and x2 that will suffice it. Oh, that's supposed to be an L. Oh my gosh. Or 2, rewrite as a parametric representation. And I'm going to abbreviate representation as rep for future. Well, now what is parametric representation? What does that mean? So in this case, in choice 1, well, some solutions could be 0, 2. Let's see, another solution could be, if that's 1, 5/3, so 1 5/3, and so on and so on. So 2 could be 3 and 4/3. 2 and 4/3, and so on. But notice the list keeps going on forever. So another way to rewrite that is, well, let's solve for one variable. So let's solve for, in this case, x1, because it's already by itself. Subtracting both sides by 3x2 should give me x1 equals 6 minus 3x sub 2. Now, what does this mean? Well, now we've introduced this new idea called a free variable. Well, what is a free variable? Well, a free variable is a variable that can take on any value. So, a variable as shown in the choice 1 option, we said one option for solving this is we can pick and choose x1s and x2s. That will suffice the equation. But notice, this goes on forever. So in order to represent this infinite, number of solutions, we represent one of those variables. So this is a definition of a parameter. We represent a free variable in terms of some other parameter. And sometimes normally we call it t. So now going back to this example, I'm going to call this example 2. This was example 2, example 3, sorry. So referring back to example 3, choice 2, we have x1 equals 6 minus 3x2. Well, let's parameterize it. So now to parameterize it, let's let x2 equal t. So that means x1 equals 6 minus 3t. And now we have parameterized this equation. Again, we do have to mention that t is a real number, or a constant. Sorry, not a constant. It's any real number. So it can be changing. Now, well, what does that look like in a bigger system? So say, for example, in a system of 3 variables, sorry. So now example 4, parameter in system of 3 variables, but with 2 equations. So, for example, let's say we have scratch that. So we're going to change my question, and I'll see if I can edit this later. But delete. So let's just try solve 3x plus 2y minus z equals 3. And they told you just to solve for this. Well, there's not much we can do. Like I said in an earlier note, before example 3, it says if there is more variables and equations, then a parametric representation may be necessary. So in this case, we have 3 variables, only 1 equation. So let's set up some parameters. I also noted that when we have 3 variables, we tend to like to isolate the z variable. So let's start that off. I'm going to do this. I'm going to change the color into pink. So now I'm going to add z on both sides. And at the same time, I'm going to subtract 3 on both sides. So that'll cancel out those 3's, cancel out these z's. So now I have z on the right side by itself. So z equals 3x plus 2y minus 3. Now, one way to parameterize this will be by introducing two parameters. So, intro two parameters. So let's let x equal s and y equal t, again where s and t are real numbers. Thus, our parametric representation is z equals 3s plus 2t minus 3, x equals s, and y equals t.